Have you ever been chatting with an AI assistant, trying to get it to do something complex, like maybe plan an entire trip?
Oh, yeah.
You ask it for flights, maybe hotels, then you change one tiny detail like the city you want to fly to, and bam,
Yeah.
suddenly it's talking about a completely different place. Or it just seems to forget everything you just said.
Right. It's that frustrating feeling where it gets confused or contradicts itself, or sometimes it just makes things up. We call them hallucinations, right?
Exactly, hallucinations or confusions. It's something, well, I think many of us have bumped into.
It really is like having this brilliant assistant who's also incredibly distractible. You tell it, book a flight to Seattle, then maybe later you just ask, hey, wasn't I departing from Boston?
Just check
And
in.
somehow it takes that as, oh, you want to change your departure city to Boston.
Oh, no.
Or even worse, like later it summarizes your trip to Seattle, but then says the flight is, I don't know, Boston to San Francisco. It's complete contradiction.
And that kind of inconsistency, well, it just makes it hard to trust them for anything really important, doesn't it?
Absolutely, you can't rely on it.
Okay, so that distinction is crucial. This whole problem of, let's call it forgetfulness and these hallucinations, it's exactly what a fascinating new development from New York University is trying to solve.
Mhm.
So today we're doing a deep dive into something they call the Task Memory Engine, or TME.
TME, right.
And this isn't just, another small tweak. The claim is it's a fundamental shift. It's
Hmm.
about teaching these large language models, LLMs, to remember more like we do.
Which could eliminate those maddening mistakes and maybe make AI genuinely dependable.
Exactly. Truly dependable, maybe for the first time in these complex tasks.
And the breakthrough here, it isn't just like a technical fix for one small thing.
Mm.
It seemed to be a whole new way for LLMs to, well, think. We're digging into a recent NYU research paper about TME.
Right.
And what it does basically is teach these AIs to build a kind of mind map of your conversation as it goes along.
A mind map. Interesting.
Yeah. So our mission today is really to unpack why LLMs stumble so badly in these back and forth multi-turn interactions and how TME offers this, well, pretty brilliant and robust solution.
Okay, so get ready, because we're going to try and understand why TME might be able to get, really remarkable results. They're talking about eliminating 100% of hallucinations in some tasks.
100%. That's a big claim.
It is, and
Yeah.
saving you tokens, too, which is always nice. But basically, teaching LLMs how to think with a much better, maybe more human-like memory.
Which, if it works, could make these AI agents way more useful and reliable in, day-to-day life.
Okay, so we've set the stage. We know the problem exists. LLMs are great for simple stuff, a quick question, a short answer.
Yeah, they shine there.
But why do they so often hit a wall when we try to get them to do something genuinely complex, like planning that whole trip or maybe scheduling a meeting over several messages? What's actually going wrong under the hood?
Well, what's really fascinating, I think, is that the core issue seems to come down to how traditional LLMs process information.
Okay.
They rely on what the researchers call a linear, unstructured context.
Linear, unstructured.
Hmm.
Okay, what does that mean in practice?
Imagine trying to organize your entire life,
Yeah.
all your plans, every change you make, every question you ask just on one giant, never-ending to-do list or scroll.
Oh, wow. Okay.
It just gets messy, incredibly fast. It's like the LLM is constantly trying to read from this scroll that just keeps unrolling and unrolling.
When it never gets, folded up or organized.
Exactly. That's pretty much what an LLM with this linear context is dealing with.
Yeah.
Just a flat, long list of everything that's been said before.
So it's just one thing piled on top of the next. How is that really different from how we process things? Because, we don't usually forget what we decided 2 minutes ago.
Well, that's the key difference, right? To humans, we don't think linearly like that. The paper mentions we use something like spatial memory. We organize goals, maybe hierarchically. We categorize, we link ideas, we prioritize.
Right, we build structure.
We build structure. Traditional LLMs, they lack that fundamental ability. And this chaotic linear context is why we see these common failures.
Okay, like what kind of failures?
Well, the big ones are hallucinations, first off. They just make up details or flat out contradict something said earlier. Like that trip planning example.
Yeah.
You changed the destination to Boston,
Mm-hmm.
and maybe the LLM adds some random, irrelevant steps.
Mm.
Then later, it summarizes the trip but contradicts itself, saying maybe the destination is Seattle, but the flight is Boston to San Francisco. Complete nonsense.
Right, because it can't reconcile the changes in its flat list.
Exactly. Then there's repeating actions suggesting things you've already done.
Oh, that's annoying.
Very. and misinterpreting revisions. A simple clarifying question like, wasn't the meeting confirmed for Thursday? Maybe it was actually set for Wednesday, could cause the LLM to mistakenly change the correct info to Thursday.
So it overcorrects based on a simple question.
Precisely. And all this constant piling on leads to what they call context overload and semantic drift. The LLM basically gets lost in its own notes.
Information overload.
Totally. It struggles to track, goals that change over time or how different parts of the task depend on each other or just simple revisions.
That makes a lot of sense. Okay, so if this flat linear memory is the big problem, what is TME actually doing differently? How does it give an LLM a better, maybe more human-like memory?
Right. That's the million-dollar question. How do you give an LLM a better memory? And TME's answer is this spatial memory framework.
Spatial memory?
Yeah, instead of that flat list, it uses graph-based structures. Think of it like a mind map, or maybe even better, like a decision tree,
Okay.
where related pieces of information are actually linked together in a structured way. Specifically, the paper mentions it uses a directed loosely-click graph, or DAGRI.
DAGRI, okay, directed acyclic, meaning information flows logically, no weird loops.
Exactly. Information flows in one direction, ensuring clarity even if the task itself gets really tangled. It avoids those confusing circular references.
So it's a fundamentally more organized way for the AI to remember things.
Yeah.
What are the actual, components that make this graph memory work?
Okay, so at its heart, there's the task memory structure, or TMS.
TMS, got it.
This is where TME actually builds that dynamic graph. It maps what you say, your inputs, to specific subtasks. And the nodes in this graph, they aren't just dumb containers.
They're smart.
Yeah, they track things like the slot, what type of info it is, like destination city. Then the value, like Seattle. It knows the parent task it belongs to, showing the hierarchy. And it even keeps a history to track changes made to that specific piece of information.
Ah, so it knows how it got to the current state.
Precisely. And this structure allows for things like shared subtasks. Maybe an ingredient used in two different recipes can be one node linked to both. And it means updates can happen globally across the whole graph almost instantly.
Okay, that sounds powerful. But what's actually reading my input, figuring out my intent, and then managing this whole sophisticated graph?
Right, that's the second key piece.
Yeah.
The Task Representation and Intent Management module, or TRIM.
TRIM. Okay, TMS and TRIM.
Yep, TRIM is basically the brain of the operation. It takes your input, which might be complex, breaks it down into smaller subtasks. Then, crucially, it classifies your intent for each subtask. Are you adding something new? Are you updating existing detail? Or are you just, checking on something?
So it understands the purpose behind my words, not just the words themselves.
Exactly. And it also infers dependencies between tasks, like if changing one thing affects another.
Okay. And you mentioned something about not needing fine-tuning.
Yeah, this is one of the most remarkable things, I think. TME works as a sort of modular controller. It transforms existing LLMs like GPT-4o. The paper uses that without needing to retrain or fine-tune the base model itself.
Wow, so it's like an add-on. Plug and play.
Pretty much. Plug and play. Which means it could potentially be integrated into current systems much more easily.
That sounds incredible, at least in theory. But how does this graph memory actually, play out in a real conversation? Can you walk us through the workflow? What happens step by step?
Absolutely. It operates in basically 5 key steps, kind of orchestrating how the LLM uses this new memory system.
Okay, step 1.
Step 1 is input decomposition. TRIM, the brain, first breaks down your input into smaller, manageable subtasks. So if you say something like, no celery, use mushrooms instead, and also search for a cake recipe.
Right, multiple things at once.
Exactly. TRIM splits that intelligently. It sees one task for the ingredient swap and a separate task for the recipe search.
Makes sense. Then what?
Step 2. Intent classification. TRIM figures out the intent for each of those subtasks. Is the mushroom thing an update to an existing ingredient? Is the cake recipe new? Or maybe you asked a question, which would be a check. It also figures out relationships, like one item replaces another.
Okay, so decomposition, then classification. Step 3.
Step 3. TMS DAG update. Based on that classified intent, TME updates the graph, the TMS. It might add new nodes for new info, or crucially, replace the value in existing nodes, like changing celery to mushrooms. It could delete nodes, or even roll back a node to a previous state if you change your mind again.
Roll back, so it remembers past states too.
Yes, because of that history tracking in the node. And importantly, it links dependencies across different tasks if needed.
Keeping everything consistent. Okay, step 4.
4 is context retrieval. And this is where that token efficiency comes in. Instead of sending the entire conversation history, the whole messy scroll,
Right.
Triumph retrieves only a compact, relevant subgraph from the TMS DAG. It might be a single node or a small cluster of related nodes. It prunes away everything irrelevant for the current step.
Ah, so it only gives the LLM what it absolutely needs right now.
Exactly. Minimal context, which leads to step 5, response generation. The LLM takes this concise, highly relevant context,
Just a subgraph.
just the subgraph, and generates its response. And because the context is clean, organized, and accurate, the response is much, much more likely to be consistent and correct. It's working with a clear picture, not a jumbled mess.
Okay, that flow makes sense. Decomposition, intent, update the graph, retrieve just what's needed, generate the response.
That's the core live.
So that's the theory. How does it actually hold up? The paper gets into some real-world scenarios, right? 4 of them.
Yes, 4 scenarios where they tested TME against other methods, like a baseline React agent, which uses that linear context.
And these scenarios really highlight the problems we face. Let's start with that classic frustration, trip planning with changes.
Right, the trip planning with revisions scenario. So the setup is user plans a trip, maybe changes the destination city. Then later, they ask that clarifying question, wasn't I departing from Boston?
Just checking again.
Just checking.
Okay.
But the traditional React-style LLM, using that linear memory, it misinterprets this. It thinks it's an update instruction. And it mistakenly changes the departure city to Boston in its memory. Then later, maybe the user asks it to search for flights from Boston to San Francisco. When React summarizes the trip, chaos.
What happens?
It hallucinates. It might say something like, okay, your destination is Seattle, which was the original correct destination before any confusion, and I found flights from Boston to San Francisco. It's a complete contradiction.
Because its linear context just couldn't reconcile the user's question, the original destination, and the later flight search, it's all jumbled.
Exactly. It's lost track. Now, how does TME handle this?
Please tell me it does better.
Much better. TME's trim module correctly classifies that wasn't I departing from Boston question as a check-in tag.
Not an update.
Not an update. So it preserves the actual departure city, let's say it was Chicago, in the graph. When it comes time to summarize, it looks at the graph, sees the destination node, clearly says Seattle, and it notes the flight search perhaps as a separate independent action.
So the summary is
Consistent and accurate. No contradictions. It correctly reports the destination and doesn't get confused by the unrelated query or flight search.
honestly, that's a huge leap in just basic reliability. It understands nuance.
It understands intent and context properly.
Okay, let's move to something maybe even more complex, with things depending on each other. The cooking example.
Ah, yes, the cooking with cross-dependencies scenario. This one's great for showing how TME handles shared information. Imagine you're telling the AI you're making soup and dumplings.
Okay.
And initially, both recipes use celery. Then you realize, wait, I don't have any celery. Let's use mushrooms instead for everything.
A global change. Use mushrooms in both the soup and the dumpling.
Right. Now, later on, you query, maybe you forgot, did I ever say to remove celery from the dumplings? A React-style LLM, again with its linear memory, might get confused. It might say something like, well, you mentioned mushrooms, but maybe celery is still supposed to be in the dumplings. It loses track of the global replacement.
So it isolates the dumpling context and forgets the overall instruction.
Kinda, yeah. And even worse if you then say something incorrect, like, I think celery was never part of the soup recipe to begin with.
Which is wrong. It was there originally.
Exactly. The React agent might actually hallucinate by just accepting your incorrect statement. It might say, okay, noted celery was never in the soup. It gets easily misled because its memory is flawed.
Wow, okay. That's bad. It's not just confused, it's gullible. How does TME handle this shared ingredient and the user potentially feeding it wrong info?
TME's solution here is really clever thanks to the graph structure. It creates a shared node in the graph for prepare celery. This single node is linked to both the soup task and the dumpling task.
Ah, one node for celery used in 2 places.
Precisely. So when you say use mushrooms instead for everything, TME finds that shared celery node and globally updates it. It marks celery as replaced by mushrooms for all linked tasks.
Okay, that makes sense. So what happens when you ask about the dumplings later?
It checks the graph, sees the celery node associated with dumplings was updated, and correctly states celery was replaced with mushrooms for all dishes, including the dumplings.
And if you try to mislead it about the soup?
It consults the history tracked within that node. It can validate, actually celery was initially planned for the soup, but it was replaced with mushrooms in round 4, or whenever the change happened.
So it maintains the correct history and resists being misled. That's actual memory.
It's robust memory, exactly. Crucial for anything involving shared resources or dependencies.
Definitely. Okay, third scenario, meeting scheduling. Always tricky with people's availability.
Right, meeting scheduling with participant conflicts. Let's say you're trying to schedule a meeting with Alice, Bob, and Carol.
Okay.
You initially propose 2 p.m., but then Carol says she can't make 2 p.m. So you say, okay, let's move the meeting to 4 p.m.
Simple change.
Seems simple, but a typical LLM using linear memory might misinterpret this. Because Carol had a conflict at 2 p.m., when you reschedule, it might incorrectly remove Carol from the participant list permanently.
What? Just because she couldn't make the first time?
Yeah, it sort of overgeneralizes the conflict. Then later, maybe you say, okay, let's just consolidate everything into a single meeting at 3 p.m. for everyone.
Explicitly including everyone.
Right. But the flawed LLM, still holding on to its incorrect assumption about Carol, hallucinates. It might schedule the 3 p.m. meeting, but omit Carol again.
Even though you said everyone. Oh, that's frustrating.
Extremely. It's stuck on its earlier incorrect state. TME, however,
Uses the graph.
uses the graph. It tracks participant nodes separately and links them to the schedule node. When the time changes, it updates the time node but retains all participant links unless explicitly told otherwise.
So Carol stays on the invite list.
Exactly.
Yeah.
And when you say consolidate for everyone at 3 p.m., it correctly updates the time and confirms the meeting includes Alice, Bob, and Carol. It reflects your intent accurately, handling the participant list independently from the time changes.
Consistency again. Okay, this last one, cart editing, sounds simpler, but you said it highlights TME's adaptability. What happened there?
Yeah, the cart editing case study is really insightful. It's a basic shopping cart task. Add items, remove items, maybe correct the quantity. Pretty straightforward.
Seems like linear memory might actually be okay for that.
And that's exactly what they found. The baseline React model, with its simple linear context, performed perfectly. No errors.
Okay, so did TME struggle?
Initially, yes, slightly. TME DAG, with its default setup designed for complex hierarchies and dependencies, it actually incurred one hallucination and one confusion.
Wait, the more sophisticated system did worse on the simple task.
Kind of, yeah. Its complex structure was almost too complex for such a flat, independent list of items. The overhead of managing the graph for simple additions and removals wasn't quite right out of the box.
Huh, that's a fascinating twist. So the complex solution isn't always better.
Not necessarily, or at least not with that adaptation. But this is where the flexibility of TME shines. The researchers realized the issue.
What did they do?
They introduced a task-specific trim adaptation. For this specific cart editing scenario, they told trim to flatten the graph structure, treat each item as basically an independent node, and just update its state directly added, removed, quantity changed.
So they simplified TME's approach for the simpler task.
Exactly. And guess what happened post-adaptation?
Let me guess. Perfect performance.
0 hallucinations, 0 confusions. It matched React's perfect score.
Wow. Okay, so that really underscores that TME isn't just one rigid structure. It's modular, it's adaptable, plug and play, like you said.
Precisely. You can potentially tailor its internal logic based on the type of task, whether it's complex with deep dependencies or relatively flat and simple.
Okay, so TME clearly makes LLMs more accurate, more reliable, less prone to making stuff up or getting confused. That's huge. But what about efficiency? Does all this graph management slow things down or use more resources? You mentioned token savings earlier.
Right, and that's another major advantage. It absolutely does make them more efficient in terms of token usage.
How much more efficient?
Well, the paper quantifies it. In one task, a form-filling scenario, TME DAG reduced the total number of tokens used by about 19.4% compared to a baseline using just flat memory.
Nearly 20%. That's pretty significant.
It is. And in rounds within that task, that involved a lot of corrections where you're constantly changing things. The savings were even higher, as much as 42.8% fewer tokens used in those correction-heavy rounds.
Wow, over 40% savings when things get messy. That's impressive. So, okay, tokens cost money, computation time, but why else do these savings matter for, the average user or developer?
Well, the efficiency comes directly from that smart context retrieval step we talked about.
Trim only grabbing the relevant subgraph.
Exactly. Instead of feeding the LLM the entire ever-growing conversation history, TME sends just the small, relevant piece of the graph. This doesn't just save computational costs, which is important, but it also means you can have much more complex interactions before hitting the LLM's context window limit.
So it scales better for really long tasks.
Greatly enhances scalability, yes. You're not wasting tokens on irrelevant history.
Yeah.
So overall, looking across all 27 user turns in the 4 scenarios they tested,
Yeah.
TME DAG achieved a 100% reduction in hallucinations. 0 hallucinations compared to 3 for the React baseline.
0.
And a 100% reduction in confusions. 0 confusions versus 5 for React. It just consistently performed better than the other methods they tested, like basic chain of thought or simple flat memory structures.
So the takeaway seems pretty clear. This graph-based memory approach really works.
It seems to be a major step forward for reliability and consistency in complex interactions.
Okay, so let's try and wrap this up. What we've really seen today is how this task memory engine, TME, with its dynamic graph-based memory, it seems poised to transform how reliable LLMs are.
Yeah, by mimicking human spatial memory, that ability to structure information, it lets these AI agents finally track goals that change over time, properly understand revisions, and crucially, avoid those really frustrating errors, the hallucinations, the confusions.
Making them potentially much more dependable for everything from, planning your vacation to maybe even complex business process automation.
Definitely opens up possibilities.
Yeah.
And the researchers aren't stopping here. They're already looking ahead.
Oh, what's next for TME?
They mentioned integrating things like graph neural networks, GNNs,
Okay.
to make the dependency inference, figuring out how tasks relate even smarter, and also enabling loop-aware reasoning for tasks that are more iterative, that might repeat steps.
So making it even more powerful for complex workflows.
That seems to be the direction.
All right, so maybe a final thought to leave our listeners with. Imagine. Imagine a world where your personal AI assistant actually remembers every single detail of your ongoing projects. It adapts seamlessly when you change your mind. It never misses a beat, never gets confused by a simple question.
That would be quite something.
What new possibilities does that really open up for how we collaborate with AI, personally, professionally, when we can finally, truly trust its memory?